Right, so weight divided by mass. So weight divided by mass equals 10. Okay, so if you rearrange that, you get weight equals mass times by 10. Okay, and that is true on Earth. Okay, so if you wanted to work out what your weight was, you would take your mass in kilograms and you times it by 10. Okay, and that would be your weight on Earth. Now, please remember that if you go to different planets and different places, even if you go really high up on Earth, like on a really high mountain, then that 10 would be slightly different. Okay, or if you're on a different planet, it would be very different. Okay, but if you wanted to find your weight on a different planet, you would end up changing your mass by a different value, and we'll talk about that later. So, in conclusion, the bigger the mass, hopefully you found the bigger the weight. And the weight of an object can be calculated by multiplying its mass in kilograms by 10. And we're going to put that on Earth, sort of in brackets, because it is different on other planets. Yep. Yeah, your weight would be different. Your mass would be exactly the same because you don't lose an arm or anything like that. So you're still made up of the same amount of matter, but your weight would be different. Yeah. Right, so example. You now have an equation, W equals mass times 10 on Earth. So calculate the weight of a 1,200 gram mass on the Earth's surface. So it has to be in kilograms when you're using your mass. So 1 kilogram is 1,000 grams, remember. So 1,200 grams is 1.2 kilograms. So if you wanted to find the weight is mass in kilograms times by 10. So 1.2 kilograms times by 10, which is 12 newtons. So the weight of the mass is 12 newtons. Right, so basically what I would say is when you're reading questions, always write down what you're given. So calculate the weight. I would say W equals question mark. That's supposed to be a question mark. And mass equals 1,200 grams, which is 1.2 kilograms. Okay, so always write down, first of all, what you're given in the question, and then just use the equation. For those of you at home, we've just found a spider. No, but I'm recording it, so they will be able to hear it afterwards. So they probably just heard you scream. That's if they watch it. Right, so let's go through example 1A together, and then I'll let you guys do B and C. So, calculate the weight of a 5 kilogram mass on the Earth's surface. So, weight is what we want to find out. Mass is in kilograms, so that's good, so we don't need to change it. So we want to find it on the Earth's surface, so we're timesing it by 10. So weight equals mass times by 10. So 5 times 10, which is 50 newtons. Okay, right. Have a go at B and C, and also have a think about question 2. Remember, you need to change grams into kilograms. So to do that, you divide by 1,000. Okay, have a go at those. Everybody done? Can you see the board okay? Is it quite bright or can you see it from, okay. Yeah, that's true.
If you're on different planets, does the weight differ because of the gravitational pull?
Yeah. Right, so I'll put up the answers so you can check as you go along. And if you get any of the answers wrong, please let me know and then we can talk about them. So part B, you should have the mass is 150 grams, so 0.15 kilograms. So the weight is 0.15 times 10, which is 1.5 newtons. Everyone get that one? Good. Okay. And calculate the weight of 20 gram mass. So the mass is 20 grams. So 0.02 kilograms. So weight is 0.02 times by 10, which is 0.2 newtons. Everyone got that? And question 2, which weighs more? As you said, it's a trick question. 1 kilogram of lead or 1 kilogram of feathers? Explain your answer. Do you want to go for it? Yeah, because they're both 1 kilogram each. Yeah. Okay, 1 kilogram of lead will be about that big. 1 kilogram of feathers would be like huge, lots and lots of sacks of feathers. Yeah, they both have 1 kilogram of matter in them. Yeah. You could do that, yeah. So you could. Yeah, yeah, you could. Yeah, you could compress them all really, really. Yeah, but you still have there'd still be more space taken up by them. But yeah, a lot less than sacks and sacks. Yes, there would be. Yeah, small. Yeah, yeah. Right. Okay. So we'll write that down. They weigh the same. They weigh the same as they are both 1 kilogram. So if you were to work out the weight of them, it'd be 1 times 10. So 10 newtons for both of them. Then the mass is the same, the weight would be the same. Yeah. And also, yeah, you think that one feather is a lot lighter than a piece of lead, but the one feather is a lot less mass than a piece of lead. Yeah. Okay, right. So I did say that we're going to talk about space now. So that 10 times it by 10 is very particular to Earth. Okay, so in space, as I said, there's different things that you times them by. We'll talk about that. So all objects of mass exert a force of gravity. The bigger the mass, the bigger the force of gravity. And the force of gravity exerted by Earth is large because it has a very big mass. The mass of the moon is smaller than that of the Earth, therefore the force of gravity on an object on the moon is smaller than it would be on the Earth. So if you've seen the videos of people walking on the moon, sort of like floating a little bit, yeah, times by a smaller amount. Yeah. So the Earth's gravitational field is the region around the Earth in which mass experiences a force due to the pull of Earth's gravity. So the Earth's gravitational field is that 10, and each planet has a different gravitational field. So what I'd like you to do, it's a bit of a pain, but copy up from your experimental results on page 7. If you can just copy the kilograms, the newtons, and the weight divided by mass. Yeah, yeah. So something like, yeah. So basically copy up your results. And I'm just going to put my demo, my ideal results down. So if it's easier, feel free to take a photo of your results and just copy them down from the photo. And it just says at the bottom, what do you notice about the last column of the table? You can just say it's constant. Yeah, it's the same. Yeah. Yeah, yeah, exactly. So remember I said that weight divided by mass is 10 on Earth. So what we say is, because that 10 we now know is a gravitational field strength, the weight divided by mass is small lowercase g, okay, where g is 10 on Earth. Okay. That's gravitational field strength, yeah, that determines the gravitational pull. Yeah. Okay. Are you still writing, Louisa? Are you still writing? Okay, right. So the ratio of weight to mass, so that means weight divided by mass, is called the gravitational field strength. It's given the symbol lowercase g and has units of newtons per kilogram, n/kg. So we've got that equation there. G is weight divided by mass. But more commonly, you see it written down as weight equals mass times by gravitational field strength. So, or shorthand, W equals mg. Yeah, if you like triangles, WMG. And you just need to remember that weight is in newtons, mass has to be in kilograms, not grams, and gravitational field strength is in newtons per kilogram. And just a reminder, the mass of an object, which is the amount of matter, always stay the same. So you could go to Pluto, you could go to Mars, your mass would be exactly the same, but your weight would be different because that depends on the gravity. Okay, so the weight of an object can change if it's moved to a different planet or the moon. A 1 kilogram bar of chocolate will weigh less on the moon than on the Earth, but it still contains the same amount of chocolate. Okay, so you still contain the same amount of matter, your bones and your bloods and your muscles and things, but your weight will be different depending on the gravity. Okay. So over the page, there are some examples of gravitational field strengths for different planets. So we've got Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. We've got the gravitational field strengths for all of those. So basically, the bigger the mass of the planet, the bigger the gravitational field strength. So, for example, an object has a mass of 20 kilograms. So that's the mass. Calculate the weight on the following planet. So I'll let you guys have a go at those A, B, and C. So you're going to be using W equals mg, and you finding the g from the table. Okay, so mass is 20 kilograms. G you find from the table. Well, you know G on Earth already. I put the answers on the board so you can check. You can see the weight on Mercury is a lot smaller than it is on Earth because Mercury is a lot smaller than Earth. And you can see the weight on Jupiter is huge compared to the Earth because Jupiter is a lot bigger mass than the Earth. Okay. I'm going to stop the theory there because I think we've done quite a lot.